This was his first microscope, right? Here was sample, and he used to, these were lenses. He used to melt glass into different convexities, concavities, shine, composition, and used to look through them, that how things appear when I look through that glass. So he used to make a convex glass, for example, and put it upon something and look into it, and that was his microscope. Right? So how simple these things were. And this was, تاسو رباب چرته لیدلې د هغه میخونه چې تاوي او تارونه کلکې او سستي دغه شی هغه ډاپ کړی دی او موږ ته رباب جوړ کوو هغه د مایکروسکوپ. This is the difference, right? So we made these things. That was from transverse of focus knob, and that was sample translator. Today you are in the highly sophisticated electron microscope. You have focus and that sample specimen translators, that how you move it under the beam in a controlled manner. Then he a little bit moved further, and he used a lamp, because the microscope needs light, and you need that light to pass through various lenses to magnify things. So he is using oil lamp. Bala force no kan. The particular divine microscope jo kare dekho, right? Our water flask and this eyepiece and objective, focusing screws, and all these things were made by him. And this barrel is nowadays called a microscope column. And that column, which was almost in air environment, nowadays for electron microscope, it has 10 power minus 6 tar evacuation. It is completely vacuum, and the internal that pressure is 10 power minus 7 tar, 10 power minus 6 Pascal. Yeah, and this is your modern microscope, which is ocular lens, which is the eyepiece. You have both eyes adjustments, dipolar head, then objective lens, nose piece, where you can change the magnifiers, right? That which lens the lenses are calibrated. That the magnification of this lens is 10 magnification, 10, and followed by the multiplication sign, 20, 30, 100. If you look into the optical microscope, and you can change, because some things are very small, so you need higher magnification. For large things, 10 is enough, and you play with that. This is the stage, the mechanical one, and these are the controllers. In the modern world, the significance of optical microscope is still there. My aim is not to teach you the optical microscope, but the principles of electron microscopes are almost similar to that old age 1600s optical microscope, right? Only the source of light, whether it was Dewar or Latin, which they use in those days, oil candles or whatever they were using, today we are using electron, and they are passing through the same process in similar control. They are passed through a sample and gives you the image. These knobs are very, very important, and don't confuse yourself with complicated terminologies and words. I am interested in measuring the thickness of this marker. But this marker is, for example, 10 micrometer in thickness. How will I measure that? I focus the microscope on my palm. It is here. I focus the microscope on the table. Then move the screw gauge and focus the top. The difference is the thickness of this marker. If it is 10 micron, if it is 20 micron, and if it is 100 micron. So the optical microscope is still used in biology and physical sciences equally. You can measure, you can determine the thicknesses of very fine features, and they are all usable throughout various disciplines of science. So their value doesn't go down with time. He was the first human to see the micro world. All these names were not known to the mankind. And it was Leeuwenhoek who white blood cells, red blood cells, yeast cells, sperm cells, and bacteria cells. So all these names came with the discovery of optical microscope. An optical microscope now come to the point. It consists of an objective lens, ocular lens, which is eyepiece, lens tube, stage, and reflector. This is the anatomy of the whole microscope. Objective lens, ocular lens, eyepieces, the column in which all these things are fitted, and stage and reflector are transmitter. You have some optical transmission in some cases, and some you have optical reflection. If the sample is geology people, when they are looking into the minerals, they make very thin sections of the samples, right? Very thin sections, and thin sections allow partial transmission of the photons, and there you go for the polarized and unpolarized light, which changes the colors of various features within the microstructure. And people, the geologists, know from the morphology, from the color, the origin, the name, the composition, grass of that particular material. So transmission optical microscopy is also there. An opaque sample which don't allow transmission, they are also investigated with optical microscopy. But please note that whenever you put an opaque sample in the microscope, you grind this wall, make it very shiny, you put it in the microscope, it will show you no features in the reflected light microscopy. And for that purpose you have to etch the sample. ETCH, etching resolves features within the sample, and then you see different morphologies in that image. The same etching is used in the scanning electron microscopy as well. Etching can be chemical, etching can be thermal. I'll explain them in the coming lecture. So, the objective lens magnifies the object placed on the stage. The magnification duty is that of the objective lens. Remember this. When the target is focused, a magnified image is observed through the ocular lens, eyepieces, right? A microscope is designed to emit light onto or through. Onto in the case of opaque sample, and through objects in case of transmission. with thin sample, thin sections, then magnifies the transmitted or reflected light with the objective and ocular lenses. So the ocular lenses may also aid to the magnification. But when it is multiplying thing in the tens, do you mean what this 10 means? 100,000, 10,000. How much difference is there? They are multiplying things. So you are getting very huge magnification. Now come to the photon. An object is here. Think very simple. Don't confuse yourself. Photons are coming from here, from here, from here, from various areas. When the beam is coming here, it is deflected more. When the beam is coming here, it is not deflected. When it is coming here, it is a little bit deflected. And you move up and the deflection will increase. The more the beam is deflected, the more magnification will occur. This is the whole game. So there is no confusion in these things. And you get a larger image here. That is the main game of microscopy. If the lens you use cause more reflection means it will form, if instead of here, it is reflected like this, then your image area is here. You see, the more the deflection, the more will be the magnification. But there is another important thing, resolution. If resolution is not there, then your magnification is of no use. When resolution is not there, when you can't resolve features, right, then magnification is of no use. If it magnifies the thing, but you can't distinguish it. These are my fingers, and these gaps are resolvable. I can separate this finger from this. But if I magnify them, and they are so blurred that I can't distinguish this finger from this, then what is the use of that magnification? Whatever I could see without magnification is not visible with magnification. This means my magnification is of no use. This is an important point. Note it. We will discuss it in the coming lectures. Optical microscope has a magnification ranging from 10 to 1500. This is the latest figure. Leeuwenhoek had achieved 266 times, and the modern microscopes with ultra fine lenses is 1500 times. E is the resolution, right? E, people usually write it with R, right? R is the resolving power of a microscope. And 0.61 into lambda or Na. Lambda is the wavelength of the radiation you use. You are using photons, you are using neutrons, you are using electrons, whatever radiation you use, its wavelength is lambda. And Na is the numerical aperture. I'm going there. And this is called the Rayleigh formula. Lambda is wavelength, lambda is 0.55 micrometer. It's used for visible light, right? 0.55, about half micrometer is the wavelength of visible light, right? When you put 0.55 here, 0.55 and 0.6, about 1.2, right? No, no, 2.5 approximately, say. And the numerical aperture is 1.2, so it will be a little bit smaller than that, say 2.4. And that will be 2.4 micrometer will be the resolution. So you can calculate the resolution when you know the numerical aperture and the wavelength of the radiation.